Welcome to MET 1010, Chapter 7 lecture, Atmospheric Circulations, where we will talk first about the scales of atmospheric circulation. How do you classify different motions in the atmosphere? We'll talk about eddies, big and small, local wind systems, global wind systems, and wrap up talking about global wind patterns and how that affects the oceans. First, we'll discuss the scales of atmospheric motion, and we have four general scales: the microscale, the mesoscale, the synoptic scale, and the global scale, with the microscale being the very smallest winds that occur over just a few kilometers and take only seconds or minutes to occur. In the mesoscale, meso meaning middle, we're talking about winds that are in the tens or hundreds of kilometers and require minutes or hours. The synoptic scale, hundreds to thousands of kilometers, and take days and weeks. And then at the global scale, the planetary scale, days to weeks and even months. And the graph illustrates that with the seconds on the bottom and the x-axis, and the scale and the y-axis, where our microscale would be small turbulent eddies, and then we transition. And you can see these winds oftentimes overlap the different scales, so it's not a definite one or the other. Sometimes they overlap, where things like tornadoes and thunderstorms, maybe water spouts or dust devils, overlap between the microscale and the mesoscale. And then at the mesoscale, we have things like land and sea breezes, as we have here in Florida, thunderstorm complexes, the Chinook or Santa Ana winds. And then at the meso to macro scale, the much larger scale, we're talking about in the synoptic level, the synoptic scale, hurricanes, tropical storms, and then the synoptic scale would be those mid-latitude cyclones or extratropical cyclones that we've talked about. And then at the global scale, we are looking at the long waves and the westerlies, or our jet streams. And I did just want to mention one other thing. That word synoptic, funny word, again, that means at the same time. So when we're looking at a synoptic scale wind or synoptic scale weather map, we're looking at a map showing what's happening with the weather across a large area at the same time. And lots of very important weather events do occur at those microscales, things like evaporation of liquid water from the Earth's surface. Another quick illustration of different types of scales. In that microscale, just a couple of meters, winds and eddies coming out of a smokestack, whereas at the mesoscale, we're talking about winds blowing over a large city, lots of big skyscrapers, so this is the big city. And then up to the synoptic scale, again, the mid-latitude or extratropical cyclone on the synoptic scale weather map.
At the microscale, you have different types of circulations: the eddy, the wind shear, and turbulence. And so an eddy is simply just a whirl of air caused by wind striking some solid object. The wind is blowing along, perhaps at a straight line. It strikes a solid object, it's deflected right or left, up or down, and it creates some type of a swirling eddy. Wind shear is something that's a little bit different. Wind shear is a change in wind speed or direction over a distance. And typically when we're talking about wind shear, and we're going to talk a lot about wind shear as you progress through the class, wind shear is a change in wind speed or a change in wind direction with height. So at the surface, the winds may be coming in, let's say, from the south and east, as they often do here in central Florida. And the mid and upper levels, they may be coming in from the south and west, and in the upper levels, they may be coming in from the west. That change in direction with height, that is going to be your wind shear. But wind shear can also be a change in wind speed. At the surface, maybe coming from the south at 10 miles per hour, but maybe at 3,000 feet above the surface coming from the south at, let's say, 30 or 40 miles per hour. And that type of wind shear can create turbulence, where the motion of the air aloft moving more quickly folds the air over. And that's what you see with this turbulence. It's an irregular or disturbed flow that creates eddies or wind gusts. And essentially, the faster winds aloft roll the air over and create these almost breaking wave-like looking cloud formations. But that up and down motion of the air, up to create the cloud and down where you don't have the cloud, that up and down motion of the air creates turbulence. And oftentimes we don't see the cloud formation. There's not enough moisture available in the mid and upper levels, and we get what's called clear air turbulence. And although those clouds look very gentle and very pretty, that up and down motion can actually be fairly violent, and sometimes that clear air turbulence is something that can be quite dangerous to aircraft.
Here's another view of the same type of cloud formation and a slightly different explanation for how it could occur with winds blowing up and over a mountain, so that's orographic lift, and then a wave being created in the atmosphere with that upward motion and then downward motion, and as waves start, that energy translates downstream and you continue to get that wave, and as those waves crest, you get those little rotors underneath it. That's the turbulence or the eddy, and that gives us these very interesting wave-shaped clouds. Also at the micro scale, but beginning to transition toward the mesoscale, desert winds such as dust devils. Now, we don't have a lot of dust devils here in Central Florida, but we do get water spouts, and they're formed essentially the same way. You have to start out with a very unstable atmosphere. That means very hot at the surface and cooler aloft, which means our air is wanting to rise. It's already beginning to move up all by itself. In the illustration, we see wind blowing over the obstruction of a couple of trees, creating the swirl, and that rising air pulls that air up in the dust devil. In the actual photograph that you see, I think the inclusion of that high-tension power line is to let us know that the wind blowing through those power poles created the swirl. The upward motion was already there because of a very hot desert surface, and that swirl and the upward motion combined to pull the dust up off the surface, and you do get the dust devil. Now, in addition to dust being in that particular funnel, as you go up the funnel, you can see the white. That's actually the condensation of whatever moisture is available. Very little, but it's there, and that condensation due to lowering pressure can be seen. The other thing in this photograph, I think, is there for a reason, is the picture of the person in very close proximity to the dust devil, letting us know that while these dust devils can be damaging to roofs and flip boats over, they're not necessarily life-threatening at short distances. Here's an animation of the formation of a dust devil, and if this is not started automatically for you, if you just click the bottom left-hand side, we'll get that animation going. In this case, we have shear in the atmosphere with winds blowing in different directions, not different speeds, but different directions with height. At the surface coming from the left, and above it coming from the right. And as the upward motion created by an unstable atmosphere, hot at the surface and cooler aloft, pulls that shear into the vertical, you get these two separate spinning tubes of air. And in those spinning tubes of air is where you're going to see your dust devil formation. So this is just another example of how these micro-scale winds can be formed as an interaction with the very hot air at the surface, the very cool air aloft, creating an unstable atmosphere or upward motion, and shear creating the dust devil. Now we'll take it up to the mesoscale. Again, the mesoscale being minutes to hours or perhaps longer, and in the tens to hundreds of meters across. And there's lots of different winds that do blow at the mesoscale. And we're going to start out talking about those winds that are created by thermal circulations. So thermal circulations are brought on by changes in air temperature, in which warm, less dense air rises and colder, more dense air sinks. These circulations are created by what we call thermal highs, which are cold core, the cold air sinking, and thermal lows, which are warm core, or the warm air rising. And so in figure A, basically we have isobaric surfaces that are even, 1,000 millibars at the surface, pretty standard, 960, 920. On temperatures, there's no temperature difference from north to south. In section B, as the sun heats up the earth, warmer to the south and cooler to the north, we see that our warm air, of course, rises, but it also expands, and so those isobaric surfaces, those pressure surfaces, they expand as well. Whereas in the north, where it's colder and the air is sinking, those pressure surfaces literally contract. So to the north in the upper levels, again, warm air is typically associated with, I should say to the south in the upper levels, warm air is associated with high pressure. To the north in the upper levels, cool air is associated with low pressure. So you have a pressure gradient and the wind begins to flow. As the wind is pulled away from high pressure in the upper levels to the south and moved into low pressure in the upper levels to the north, of course, pressure decreases at the surface under the high and increases in the surface under the low, and that completes your thermal circulation. So in A, isobaric surfaces lie parallel to the surface with no temperature or pressure gradient. Warming the air to the south causes it to expand, thickness increases, while cooling to the south causes it to contract, thickness decreases. Pressure gradient force from high pressure aloft to low pressure aloft causes air to pile up in the north, increasing surface pressure, while the PGF evacuates air in the south, decreasing surface pressure. The pressure gradient force at the surface moves cool air from the north to the south to be warmed, becoming less dense and rising in the atmosphere. And in this case, the wind's going to blow from north to south. We see those mesoscale thermal circulations play out most days in our warm season over central Florida, where the peninsula of Florida is warm during the day. Of course, land heats up more quickly than water, so it heats up, and that's where you get your thermal low at the surface, and the air over the water remains cool, and that's where you get your thermal high. The land sea breeze circulation is a thermal circulation at the mesoscale. The differential heating of land and water causes the land to heat up more quickly during the day than what happens to the air over the sea. So while the land may go from 72 degrees in the morning to 90 to 95 degrees in the afternoon, the air over the ocean probably won't change much more than 1 or 2 degrees. So you get a big warm up over land, cooler air over the ocean. A thermal low then forms over the warmer land surface, and a thermal high forms over the cooler sea surface. And the pressure gradient force moves air from the sea onshore to land. We call that an onshore wind. That's that cooler air, the sea breeze coming off the Atlantic, or in the case of the Gulf of Mexico, off the Gulf, and that sea breeze moves inland. Now, expansion of the isobaric surfaces or pressure surfaces, because again, warmer air is thicker, and contraction of the isobaric surfaces over the water, because cooler air is thinner, creates a pressure gradient force aloft, just like we saw in the previous slide, and that moves air from high pressure aloft to low pressure aloft, and that completes our thermal circulation. Now, simply the opposite occurs at night, forcing a land breeze, not usually as strong, but the earth cools rapidly at night over land and doesn't really change a lot at night over the water, and you get a reverse occurring in the land breeze. And you can see that with the sea breeze, cumulus clouds form over the thermal low over land during the day, and with the land breeze, those cumulus clouds form just offshore. So you wake up in the morning on a warm summer day in central Florida, we may not have cumulus clouds. As the afternoon progresses, they develop and build with that thermal low. At night, things begin to clear on out, but if you get up very early in the morning and go to the beach, oftentimes you see that line of cumulus clouds just offshore. That's a function of the land breeze. Now, sea and land breezes also occur near the shores of large lakes in Florida and other areas where we have large lakes. So here are some fairly good illustrations of the land and sea breeze. So the leading edge of the sea breeze, the inland moving sea breeze, it's what's known as the sea breeze front. And it's really just like any other cold front or warm front or even stationary front, because along that front, winds are converging, because the sea breeze is coming in from the east, or in the case of the Gulf sea breeze in the west, and it's converging on the other winds blowing across the peninsula. Wherever you have convergence, you get uplift, and that's how you get those clouds forming and eventually the thunderstorms. Interestingly enough, the temperature gradient across that sea breeze can be as much as 9 degrees Fahrenheit. So a 92-degree day in Orlando may mean in Titusville or Cocoa Beach, we're really only talking about temperatures maybe at 83 degrees. So it's a significant difference. Why people talk about the sea breezes cooling the areas at the coastline. And the air along that sea breeze is typically what we call conditionally unstable. We talked about that with the last lecture, where as air is forced to rise, eventually it gets to a point where free convection takes over and thunderstorms develop. So we can see from our upper right-hand picture, the Atlantic sea breeze, the Gulf sea breeze, the winds move inland, and literally those two sea breezes converge right up and down the spine of central Florida, and that's where we get our typical thunderstorms developing every afternoon, 2 or 3 o'clock in the afternoon. The radar images at the bottom left and bottom right, two different images from different times, literally showing on radar that sea breeze front as it develops and moves inland. And of course, the picture in the middle, a good example of a late afternoon thunderstorm developing along a sea breeze. So the sea breeze and the land breeze circulations represent daily reversal of winds, a diurnal reversal of wind. It's a daily occurrence where the winds reverse. Also at the mesoscale are mountain and valley breezes. And the valley breeze, the daily heating, causes the expansion and upward vertical motion over the side of the mountain, and clouds and sometimes rain. So remember, we talked about the atmosphere, we talked about controls of temperature. That thinner air at higher elevations allows the land to heat up and cool off more quickly, because there's less air molecules to scatter or disrupt the incoming solar radiation. So During the afternoon, the side of the mountain will likely warm up more quickly, creating a thermal low, drawing that air up. Whereas the mountain breeze at night, that mountain slope will cool off more quickly at higher elevations. Again, the same reason, the air is thinner up there, and that cool air will then flow downhill under the force of gravity. So a valley breeze happens during the day with wind blowing uphill, and then the mountain breeze occurs at night with those mountain slopes cooling off quickly and that cold air moving downhill at the force of gravity. Those nighttime mountain breezes are sometimes called gravity winds or drainage winds because gravity causes that cold air to drain downhill. A different type of gravity wind, but also happening for the same reason, gravity pulling colder air downhill, and also at the mesoscale is what's known as a katabatic wind. Katabatic, not too different from the word adiabatic. So a katabatic wind is a downslope wind, but it's going to be typically stronger than those mountain breezes. Those mountain breezes at night are fairly gentle, but the katabatic wind is quite a bit stronger. You have to have a high plateau or an area at high elevation where cold air can sit for a very long time and become colder and colder. And then once that colder air begins to build up and thicken, it will literally flow over the peaks at the top of the mountain and flow downhill, and the force of compression will warm it very quickly. So a katabatic wind is the technical name for a drainage wind or also a gravity wind. That is a wind that carries cold, high-density, colder air is denser, cold, high-density air from higher elevations down the slope under the force of gravity. Sometimes these winds are also called fall winds or Foehn winds, which is Foehn is a German word for referring to gravity again. So the ideal setting, as you can see in the illustration, is an elevated plateau that's snow-covered and therefore cools the air at high elevation. As the air begins to descend through the gaps and the valleys at the top of the plateau, it can be channeled and can actually accelerate under the force of gravity. And these katabatic winds can be quite strong. As a matter of fact, in Antarctica, they can take up to a hurricane force wind speeds. Another interesting name of a wind, which is also a mesoscale wind, but it's also a gravity or a fall or a drainage wind or a Foehn wind, is called a Chinook wind. Now, Chinook is a Native American name, and it was given to these very dry, warm winds that come down the leeward side of mountains, and Chinook is the Native American term for snow eater, and it's because we could have snow on the leeward side of the mountain, and this warm, dry wind comes down, and literally the snow doesn't melt, it evaporates because how warm and dry the air is. So Chinook winds occur due to orographic lift, and we've had this illustration of the wind, the rain shadow, as winds are lifted orographically. So orographic lift cools air on the windward side of the mountain until it reaches 100% humidity. That's where our cloud forms. Of course, that's saturation, condensation. Condensation, the formation of clouds, possibly even rain or snow, robs the air of moisture while it adds heat. Remember, condensation is a warming process. The air is then forced down the mountain on the leeward side, and it warms at the dry adiabatic lapse rate, and that heats it up and drops its relative humidity. So those Chinook winds are very warm and dry and are able to eat the snow if it exists on that leeward side of the mountain. Now, in Boulder, Colorado, we have winds that are so strong that those Chinook winds oftentimes bring blowing debris with them, and homes on that side of the mountain will have shutters to protect their windows. And here's another example, another illustration of that Chinook wind where the wind is forced up the windward side. The moist air is robbed of its humidity with cloud formation. Condensation warms the air as it's forced back down the leeward side of the mountain. You get a warm, dry air, and you can have a significant difference in temperature between that warm and dry air on what's actually happening at the surface, and those Chinook winds can be quite strong. The next wind is a Santa Ana wind, and the Santa Ana is really somewhere between your mesoscale and your synoptic scale. Not quite weather map size, but beginning to get there. A warm, dry wind that east or northeast, that blows from the east or northeast into Southern California. So high pressure over the high desert of the Four Corners and Nevada creates a downslope wind that's literally forced through the mountain canyons in eastern parts of California, southeastern parts of California, the Santa Ana Canyon, and compressional heating, as that wind is forced downhill, heats that air and dries it out. As it's funneled through the canyons, it picks up speed and actually becomes a major wildfire threat to that region. So again, the Santa Ana wind only happens here in the southwest corner of the United States, but it's a big dome of cold, high pressure over the high plateau, the high desert plateau. That high pressure and the clockwise flow around it forces winds to the Santa Ana passes. They compress, heat, and dry. It's some very fast offshore moving winds that the surfers in Southern California love because it's a warm wind and it blows offshore and cleans up the surf, but it's also a major wildfire threat in the area. Here's a slightly different view of that Santa Ana wind. Again, you get out of Los Angeles and Southern California, you get to the coastal ranges, and then you get to the High Sierra, and back behind the High Sierra, the land mass is really, well, the elevation's quite high, and it's a cold area, big dome of high pressure. High pressure, the air sinks and moves outward, so as it moves outward, it has to funnel its way through these gaps in the mountains, and as it comes downhill from those higher elevations, it warms and dries and creates those strong Santa Ana winds, and a big-time fire threat in Southern California. We see that every year when the Santa Anas kick up. Another wind that's transitional from mesoscale to synoptic, but really when you start looking at the region here, it's going to fall into the synoptic scale, is the monsoon wind system. Now, monsoon, when you hear that term, most people just think rain or lots of rain. It's a monsoon out there. Well, monsoon actually doesn't refer to rain at all. It refers to a seasonal reversal of winds. Monsoon means seasonal reversal of winds. Now, in Florida, we have a daily monsoon, meaning during the day we have an onshore flow, showers and thunderstorms, and then at night we have an offshore flow with the land breeze. In the Asian monsoon, the most famous monsoon, it's really seasonal, where in the summertime, we have an onshore flow coming off the Indian Ocean, bringing lots and lots of warm, humid air and lots of rain. And then in the wintertime, the high pressure, the cold high pressure from the Tibetan Plateau, again, another very high plateau, forces air down the mountains, the Himalayas, literally into India and South Asia, and that air is heated and dried and creates a season of very, very dry air. So monsoon wind system is a seasonal reversal of winds, a wind system that changes direction seasonally, blowing from one direction in the summer and the opposite in the winter. In the Asian monsoon, again, the winter months bring high pressure and an offshore flow, while the summer months bring low pressure and an onshore flow. And here is how that all that rain plays out. So June, July, we're talking about 120 to 140 inches of rain in India and South Asia. That is when there is low pressure over the Himalayas. Again, the Himalayas represent a high elevation heat source. It's very high up. It heats up very quickly. We get this seasonal low that forms there, and it continues to suck the wind off the Indian Ocean. That warm, moist flow drops all that rain. And you get into October, November, the rain almost cuts off. And in January, there's virtually none, because at that point, we're talking about high pressure that sets up over the Tibetan Plateau. And then you get this tremendous offshore flow. As it comes down the Himalayas, it heats up, it dries out, and you have very, very little rain in the wintertime.
When winds throughout the world are averaged over time, the local patterns tend to vanish, and what you're left with is a global scale pattern known as the general circulation of the atmosphere. Now, the cause of the general circulation of the atmosphere, all that wind swirling over the globe, is the same cause as many things in meteorology: unequal heating of the Earth's surface. The direct rays, insolation, incoming solar radiation, the direct rays of the sun strike the equator at a very high angle and warm it up, and the direct rays of the sun strike the poles at a very low angle, and the poles remain cold. So unequal heating of the Earth's surface has the effect of atmospheric heat transport, where the very warm air at the equator, where there is a heat surplus, moves northward, and the very cold air at the poles, where there is a heat deficit, moves southward toward the equator. So warm air moves toward the poles, cold air moves toward the equators. And oceans also help to transport heat from the equator to the poles and back again. As often is the case in the study of atmospheric sciences, we have to work with a conceptual model, not
quite what actually happens in the atmosphere, but a human construct that we can create that closely resembles the atmosphere. We're going to talk about the single cell model and the 3-cell model. And the single cell model is not a good representation of the atmosphere. This is as simple as it gets. Imagine an Earth that is straight up and down, no tilt in the axis, no angle of inclination, an Earth that is completely featureless, so covered with a flat sea, no waves, and an Earth that is not spinning. There's no Coriolis because the Earth is not spinning. So uniformly covered with water, sun always directly over the equator, no seasons, and it does not rotate the Earth, so no Coriolis. In this situation, we'd have one thermally driven convection cell in each hemisphere, where the hot tropics would produce a belt of low pressure or upward motion, and the cold poles would produce an area of high pressure or downward motion. And at the surface, wind would blow from the high pressure at the surface to low pressure at the equator from north to south, bringing cold air back south. And in the upper levels of the atmosphere, the warmer air would blow north. And that one circulation cell in each hemisphere would be known as a Hadley cell. And again, those assumptions don't work, so we'll look at a different model of the global circulation of the atmosphere. There is a lot going on in this 3-cell model of the atmosphere, and this is one of those basic concepts in meteorology that then lends itself to climatology that you'll simply have to get a handle on and a grasp on what's happening. And so we have 3 different cells, and if you can see on the left side of the illustration, the Hadley cell, a Ferrel cell, and a polar cell. Now we're going to go through these one at a time, starting with the Hadley, then polar, then Ferrel cell. Then at the surface, those cells, those convection cells, create winds. The trade winds, which is one of the greatest prevailing winds in the atmosphere. The westerlies, also one of the greatest prevailing winds in the atmosphere. Then the polar easterlies, which aren't nearly as significant. So if we allow for a uniform Earth, you can see this Earth doesn't have any land over it, no continents, no mountains, and it's covered with water. But we do allow the Earth to spin. So it's straight up and down, no angle of inclination, but we do allow for the rotation of the Earth and therefore Coriolis. We get a closer approximation of the real atmosphere. So let's start at the equator. We know the equator is hot. We know that hot air rises, and so as hot air rises, it gives up its humidity in the form of condensation, cloud formation, and precipitation. So at the equator, we have a belt. All around the equator, we have a belt of low pressure where air is rising and you get cloudy, wet weather. That's why we have the Amazon. That's why we have the Congo. All right? That belt, if you look on the right side of our planet, is called the Intertropical Convergence Zone, or the ITCZ. That is our area of low pressure. Now, in the atmosphere, that warm, moist air rises. As it gets up in the atmosphere, it is robbed of its humidity. It moves north, as you can see, and then begins to cool as it moves north, and it sinks. So the Hadley cell is composed of a belt of low pressure at the equator, and then secondly, a belt of high pressure at about 30 degrees north latitude. And that belt of high pressure at about 30 degrees north latitude is known as the subtropical highs. Sometimes we talk about the Bermuda high pressure, the Bermuda Azores high pressure. That's part of a belt of subtropical highs. So at the surface, we have a belt of lows, the intertropical convergence zone, and we have a belt of highs, the subtropical highs. Next, we'll take a look at the polar cell. So we're going to go to the North Pole here. And because of the very cold air at the poles, the air is dense and therefore it sinks to the surface. And air sinking at the surface is high pressure. And of course, as always, air moves outward and clockwise away from high pressure. And so what that means is you get this northeast wind coming down from the poles, and that northeast wind then converges on the southwest wind, the westerlies, coming up from the subtropical high pressure. So that area of convergence creates a belt of low pressure. Our first belt of low pressure was created because of heat at the equator. Our second belt of low pressure at about 50 to 60 degrees north and south latitude is created as winds converge on what is known as the polar front. And of course, convergence at the surface means uplift. So this is also an area where we have cloud showers and possibly thunderstorms. And the polar front really is the main location where most of our mid-latitude cyclones come from. And we'll talk about that in Chapter 8. The bottom line is the polar cell and the
Hadley cell are both thermally driven convection cells, with cold air sinking at the North Pole driving the polar cell and warm air rising at the equator driving the Hadley cell. In between the two, the Ferrel cell, which goes in the opposite direction, is being mechanically driven by the rising, or the sinking air that is, at the subtropical highs and the rising air at the polar fronts. And so now we have the Hadley cell, the Ferrel cell, and the polar cell, and these different winds generating different parts of the globe in terms of climate. So at the subtropical belt of high pressure, sinking air creates a dry and a fair weather scenario. And at 30 degrees north latitude and 30 degrees south latitude, that is where you typically find the world's great deserts. In addition to that, of course, at the belt of low pressure known as the ITCZ, the Intertropical Convergence Zone, rising air creates showers and thunderstorms, and that's where you find the very wet and rainy regions, and along the equators where you're going to find the Amazon and the Congo. And then as you move south, 30 degrees south latitude is also where you find the world's deserts. And of course, the great desert of the world is going to be at the South Pole, Antarctica, where it's very, very cold, and sinking air keeps the weather generally dry. We don't get a lot of precipitation there, and it's one of the world's great deserts. Other factors within the three-cell model, we have the horse latitudes and the doldrums. The horse latitudes at that subtropical high where the wind's very light, so old-time sailing ships would be becalmed. They would not be able to make much headway because of a lack of wind. And then the doldrums down at the equator, where weather conditions are essentially the same all of the time, hot, humid, and stormy, so there's not a whole lot of change. And again, this three-cell model dictates the general climate features that we find around the globe.
Let's now talk about how that global atmospheric circulation affects our surface winds. And one of the first things you need to understand, because the northern hemisphere has so much land, and we know that land and water heat up and cool off differently, it does create some fluctuations in some of these wind patterns. The first one being the ITCZ shifts with the seasons, meaning in the summer seasons, as you can see on the left-hand side in this illustration, that thermal low over the Tibetan Plateau pulls the ITCZ well to the north. And even the thermal low over the southwest desert of the continental United States pulls the ITCZ a little bit further to the north. So you can see that ITCZ is a little north of the equator in the summertime. In the wintertime, it drops back down toward the equator, but you can also see where it's pulled further south of the equator, where the Australian thermal low will develop, and even over Africa and over South America pulls that ITC to the south. Now, one of the big prevailing pressure patterns that creates a lot of the wind that we deal with is going to be those subtropical highs. So let's look at the summertime first on the the wintertime, first on the right, where you have almost a continuous stream of those subtropical highs. The Pacific, the Bermuda, even the Siberian and the Canadian high are near the subtropics, and those high pressure cells create these constant clockwise turning of winds, bringing us the trade winds in the lower latitudes, and then also the westerly winds in the upper latitudes. In the summertime, we do get that thermal low over Asia and that thermal low over the southwestern desert, and that changes the patterns just a little bit. But you can see that Bermuda high pressure, whether it's shifted a little bit to the west in the summer or back to the east in the winter, is very significant in bringing that hot, muggy weather to the eastern United States. So how does the general circulation of the atmosphere affect the general precipitation patterns of the globe? And if you watch that YouTube video from 2 slides ago, you'd have some idea. But look at this illustration on the right. You have the globe. You have your ITCZ in the equatorial zone, those lows, that belt of low pressure along the equator. And of course, that produces hot, humid, and rainy conditions. And so over Africa, you have the Congo region, and over South America, you have the Amazon region. And then if you go north in the northern hemisphere, that belt at 30 degrees, the subtropical high, that's where you get sub-Saharan Africa and the Middle East, and even the deserts and the desertification of Asia, including parts of India. And that is, again, because of sinking air at the subtropical high
high pressure, fair weather, very little rainfall. And then once you get up to about 50 to 60 degrees, you start getting those subpolar lows, that polar front, and once again you get showery, rainy weather. And that's where you get the more temperate zones and the wet weather of Europe and northern parts of Asia and including places like Russia, but also in the continental United States. We have the wetter regions of the continental U.S. and up into Canada. And then, of course, at the polar regions, once again, that's high pressure, fair weather. So really the world's greatest deserts are at the poles, where there's very, very little precipitation because of that high pressure. And we can see in this illustration to the left where our Bermuda High and our Pacific High help to create nice, warm, humid air across the southeast, but much cooler and drier air across the west coast of the United States. Now, in terms of the global circulation of the atmosphere and the larger scale, the global scale, now we're talking about the westerlies in the upper levels of the atmosphere. So now we're beginning to talk about not the westerlies at the surface, but the westerlies in the upper levels are jet streams. So the jet stream is a relatively narrow band of strong wind in the upper levels of the atmosphere. The winds blow from west to east in the jet stream, often shifting a little bit north and south, meaning jet stream winds can be almost due west to east. We call that zonal, but very oftentimes they get wavy and they dip north and they dip south and pull north, and that's called meridional, but generally the flow is from west to east. And these jet streams literally follow boundaries in the atmosphere between hot air and cold air. Since these hot air and cold air boundaries are most pronounced in the wintertime, jet streams are typically strongest in the wintertime. And you can see where the looping pattern of that polar jet oftentimes plays a very important role in global heat transport, as it does move cold air from north to south. That's how we get our cold air in the wintertime here in Florida. The jet stream dips nice and far south and brings a blast of cold air for a day or two, but also pulls warm air south to north as well. Not only is there a polar jet or a polar jet stream, there's also a subtropical jet that's not always there. It's more intermittent, but largely it is in place. But I also want to point out that the illustration shows these as almost continuous rivers of air. Sometimes these rivers are broken down in terms of their speeds, with faster areas in some spots called jet streaks and slower areas in other locations. These are the illustrations as to why the jet streams occur and how they occur. So the subtropical jets typically located about 30 degrees latitude, just on the poleward side of the Hadley cell, and the polar front jet is located between 50 and 60 degrees latitude on the poleward side of that Ferrel cell. So I want to start out with this illustration on the right. If you look at this, we'll start at the equator to the far right. That's where we have that belt of low pressure. That's where the air is warmest at the equator. And so what happens to the atmosphere? It is thickest. The atmosphere from the surface to the top of the troposphere to the tropopause. So just imagine that shaded purple surface you see at the top of the illustration being the tropopause. The atmosphere is thickest where it's warmest at the equator, and then it gets thinner as you get poleward where the weather is colder. So that transition zone between the warm air and the cold air is going to be that 30 degrees north latitude. And what happens to warm air as it moves toward the cold air, as that high pressure aloft moves toward that low pressure aloft? Well, yes, the wind turns to the right because of Coriolis. So we start out moving north, it turns to the right because of Coriolis, and the difference between that warm air and cold air creating that subtropical jet. Now, between 30 and about 50 to 60 degrees north latitude, there again you have a very big difference between warmer, or say moderate air over the mid-latitudes, and the colder polar air, and that once again creates the jet stream, and the deflection to the right creates the polar jet. You can see a very similar illustration of this to the left, where we have the cold air to the north, the warm air to the south, the thicker atmosphere to the south, the thinner atmosphere to the north, and that movement of air from the warmer to the colder and turning right because of Coriolis, creating those stronger winds in the upper levels of the atmosphere. At the global scale, these larger scale wind patterns also affect the oceans and create our ocean currents. So as wind blows over the ocean, it causes the surface of the water to be dragged along with it. And that surface being dragged along with the wind because of friction pulls water at deeper and deeper levels along with it. So in this way, the general wind flow around the globe starts the major ocean currents moving.
Higher friction of the water means that it's not going to move as quickly as the wind. So the wind may be blowing at 15 or 20 miles per hour, and the water underlying that wind may only blow at 2 to 5 to 6 or 8 miles per hour. But in this way, with that those belts of high pressure at the 30 degrees north and 30 degrees south lines, those belts of high pressure, whether they're Bermuda Azores high to the north, in the North Atlantic or the Pacific high in the North Pacific, the clockwise flow around those belts of high pressure, both northern hemisphere and southern hemisphere. Of course, in the southern hemisphere, it's a counterclockwise flow around high pressure. Those high pressure cells and the winds around high pressure cause the ocean currents to loop as well. And those loops are almost closed, not quite closed. Ocean currents that loop in the major ocean basins, North Atlantic, North Pacific, South Atlantic, and the Indian Ocean, those loops are called gyres, G-Y-R-E-S. So on the eastern edge of continents, the eastern edge of the continent, like here on the east coast of the United States, poleward moving currents move warm water to higher latitudes like the Gulf Stream, and in the Pacific, the Kuroshio Current. On the western sides of continents, equatorward moving currents move cold or cool water to the lower latitudes. That's like the California Current, or on the west side of Africa, the Bengal currents. That's where cold water is moved toward the equator. 40% of the total heat transport in the northern hemisphere occurs because of ocean currents. It's higher in the southern hemisphere because there's just more water down there. This is what those ocean currents look like, with the North Atlantic Current and the Gulf Stream taking warm air north. And understand the dramatic impact of this. Look at where the Western Europe is, whether it's France or the UK, at the latitude it exists. Take that straight across the west to Canada, and you can see that that's like central and northern Canada, very frigidly cold areas of Canada. The reason why Western Europe is not nearly as cold as a climate is because that Gulf Stream pulls a tremendous amount of warm water toward Western Europe. Similar situation. Why is it always so cold in the water in California? San Francisco can be chilly, downright cold in the summertime. As a matter of fact, Mark Twain said the longest winter he ever spent was one summer in San Francisco. And again, it's that California current bringing cold air from the north to the south. So these ocean currents created by wind patterns have a major impact on transferring heat north and south.
It's called the Great Ocean Conveyor, and it's one of the most powerful forces on the planet. It's made up of warm currents which travel at the surface, whilst at the bottom of the ocean are much colder currents. The conveyor transports oxygen, nutrients and warmth around the world. It's vital to the health of all life on Earth. Yet the conveyor wouldn't keep flowing if it wasn't for what happens in the cold northern oceans. This is where the surface water sinks to join the deep water currents. The sinking happens because the water's very cold. This makes it dense and heavy, so it plunges to the bottom of the ocean. And it's this sinking water which keeps the entire conveyor moving. As it travels south, it hugs the ocean floor until it warms at the equator, where it eventually rises to complete the circuit. Without cold water sinking at the poles, the ocean conveyor would collapse. The sea would no longer be supplied with oxygen and nutrients. It would become stagnant and lifeless. It takes roughly 1,000 years for water to circulate all the way around the conveyor. And this global network of currents controls the well-being of the entire planet. Without it, our world simply wouldn't function.
We'll wrap up our conversation about atmospheric circulations and Chapter 7 with a conversation about teleconnections. Now, teleconnections, something that scientists really have only got a good handle on, have only achieved a good handle on over maybe the last 20 to 30 years, and really a teleconnection, which is the ocean-atmosphere interaction in which sea surface temperatures in one part of the globe literally influence weather patterns in other parts of the globe. Teleconnections really could be an entire course in the study of advanced atmospheric sciences. So we're just going to really touch on this and talk briefly about what is the most famous teleconnection, which is the El Niño Southern Oscillation. So teleconnections, again, ocean-atmosphere interactions where sea surface temperatures in one spot change weather patterns in other spots. The most famous being the El Niño Southern Oscillation, where El Niño is the warming of the eastern equatorial Pacific Ocean. That occurs on about intervals of maybe 2 to 7 years, and El Niño is caused by the flipping of surface pressure patterns at opposite sides of the equatorial Pacific. That's the Southern Oscillation. Now, non-El Niño years, and what sometimes referred to as La Niña, although I think La Niña is really falling out of favor with the scientific community. Non-El Niño is what we'd find typically in the equatorial Pacific Ocean, and La Niña would be following an El Niño where pressure changes strengthen easterly trades, and then large amounts of cold water move west around across the equatorial Pacific. So we can talk about all these different pressure patterns, how they affect different parts of the world, and why. The key to the El Niño teleconnection will be the pressure patterns. And in non-El Niño conditions, or just your typical conditions, you have low pressure that's going to be on the western side of the Pacific Ocean and high pressure on the eastern side of the Pacific Ocean. And that's completely about global circulations, counterclockwise flow south of the equator, clockwise flow north of the equator, bringing cold water from the north along North America and cold water from the south along South America, creating sinking air and high pressure on the eastern side of the Pacific Basin, and then the warmer water on the western side. Now, this illustration does not do the Pacific Ocean justice. The Pacific Ocean is just so massive, and it's why this ability of a change in temperature on the Pacific Ocean to affect weather in other areas, because when you change the temperature over the eastern equatorial Pacific, it's such a massive region of oceanic real estate that it can literally affect other parts of the world. So, non-El Niño conditions, low pressure west, rising air, Indonesia, Jakarta, even parts of Australia, nice and wet, nice and rainy, exactly what you'd expect. All right, and then high pressure on the eastern side, sinking air, cold water, upwelling, and you can see that thermocline. That's underneath the ocean. That's the line of temperature where warm water is very deep in the west, and cold water is very shallow in the east. In a El Niño event, the pressure pattern flips. Large global scale shifts allowed the low pressure to shift to the eastern side, so we get low pressure or atmospheric pressure falling off the coast of Ecuador and Peru, and atmospheric pressure rising along Indonesia. And so that sinking air to the west and the rising air to the east literally causes a strong countercurrent to develop. Look at the northern illustration. That high pressure and low pressure, not only does it create winds, trade winds, but it pushes that water back. It pushes that water across the Pacific Ocean, so all the warm water is literally piled up to the west. Well, when that atmospheric pressure pattern flips, that warm water that's piled up to the west literally flows downstream and to the east, and water along the coastline of South America that is typically very, very cold warms up very, very quickly. Warmer water, no upwelling, no cold water, no nutrients, no fish. That's very bad for the Ecuadorian and Peruvian fishermen. But not only that, you see this dramatic change in weather conditions, and not just weather conditions along the coast of South America, but across other parts of the equatorial regions as well. So again, on the bottom we have our El Niño conditions on the left and our non-El Niño, maybe even La Niña conditions to the right. You have your low pressure that has formed basically in non-El Niño conditions over Indonesia. This is going to be on the right at the equatorial Pacific, and high pressure just off the coast of Ecuador. And you have that water being pushed back toward the west, and all the warm water pooling and that low pressure to the west creating rising air. So that is your non-El Nino conditions or La Nina conditions. And then on the left, that pressure pattern flips and all that warm water flows back down toward South America and Central America, and you get all that warm water in the equatorial Pacific Ocean, the eastern equatorial Pacific Ocean. So how does that affect the atmosphere so that it actually has a change in weather patterns? Well, if you look at the La Nina or non-El Nino conditions, the typical jet stream pattern is for the northern branch of the jet stream to be really quite far north and dip down south over the central parts of North America, right on down, digging down in the Front Range of the Rockies and bringing cold air, oftentimes as far south as the southeastern states. That's a typical pattern. When you get this very warm air in the equatorial parts of the eastern Pacific Ocean, look at our left. Warm air causes that air to thicken. The cold air to the north, the air is thinner. So you literally get a stronger jet stream that is displaced well to the south. So that southern branch of the jet stream, not only is it much stronger, but it's displaced well to the south, bringing very wet weather right across the southern tier, northern parts of New Mexico and the south eastern states. And so that is the primary effect. And that southern branch of the jet stream being stronger and displaced far to the south in El Nino years causes very active weather patterns along that region. Now, interestingly enough, we'll learn when we talk about tropical storm formation that stronger jet stream to the south, that southern branch of the jet, actually results in fewer hurricanes when there's an El Nino year. There are other of these teleconnections, the North Atlantic Oscillation, the Arctic Oscillation, the Pacific Decadal Oscillation, some having changes in weather patterns over months and even years in some cases. But the concept of teleconnections, sort of a new part of meteorology and climatology, and the real opportunity for study in the future.
So that wraps up Chapter 7 from Introduction to Meteorology on Atmospheric Circulations. Coming up next is Chapter 8, Air Masses, Fronts, and the Mid-Latitude Cyclone.